let us have a look at a problem on a half-wave rectifier which is supplying an RC load. Now the capacitor here will help us to shapen the output voltage into a DC by removing the ripple in the voltages. Now we consider that the source voltage is 140 sine omega t and the value of the resistance is 10 kilo ohm and the value of the capacitance is 40 microfarad. In this case, if you wanted to get the average output voltage and also the kind of voltage ripple we have in the output voltage, first of all, let's have a look at the responses of the half-wave rectifier. Now in this figure, you see that the source voltage is in yellow color, that is a pure sinusoidal voltage, but you will be getting the output voltage, that is voltage across the resistor, to be not just purely oscillating the way we have in a resistive load, because if you look at in the beginning stage where the source voltage will be higher than the load voltage, that is when you will have diode conducting and the capacitor start charging. The moment the capacitor charges to the maximum voltage, then your source voltage is reducing, but the capacitor voltage will be slowly reducing because of its opposition to the sudden changes in the voltages or the charge in the capacitor. So due to charge in the capacitor, the voltage across the capacitor is going slow, whereas the source voltage is now going low. That is when the diode will be off. So that is the case where your capacitor will be supplying your load and the voltage across that will be slowly reducing. And then the diode will not conduct until this point because the source voltage is lesser than the capacitor voltage. This is the time at which your diode starts conducting again. So now let us say this is the time, we call it as time at which diode starts conducting. So this is where your diode conducts. Now if you know the time at which diode is conducting, that is how you will be able to calculate an average value, because this is the voltage you wanted to calculate. Now in order to get the average output voltage of a half-wave rectifier which is feeding an RC circuit or RC load, it is very important to know the time at which diode starts conducting. Forget about this transient part, but in the steady state, if you wanted to know the time at which the diode starts conducting, this is what is the equation we use, boundary conditions, where you say that my output voltage at time t1, let us consider that this time is t1, is exactly same as the same voltage after one cycle. So this is basically t1 plus the total time period t. If you use that output voltage expression to be same at t1 and t1 plus t and simplify that equation, that is when you will get to know this particular expression which can be solved. You can see that in this equation, you know everything except the value of t1. The value of tau is nothing but the time constant of the RC circuit there. So if you solve this particular equation, it is a kind of a nonlinear equation where you need to solve it by trial and error. But one hint for us is that it is very important that value of t1 is between 0 and time t by 4. The total time period, 1/4 of that total time period. So this will be in this range, 0 and t by 4. So if you substitute the numbers within that range with some tolerance, you will be able to get the value of t1 as 3.4 milliseconds. So the moment you have the t1 as 3.4 milliseconds, then that will be enough for us to calculate the average value of the output voltage, whereas this is the expression that we derive in calculating the average output voltage for an RC load in case of a half-wave rectifier. So now we know that the value of t1, and you have to average out the voltage from t1 to t1 plus t, because that is where your voltage is oscillating with. So we'll be able to get that average voltage value as 137 volts. So what is critical for us here is to get the value of t1. And in fact, the value of t1 will be ranging between 0 and t by 4, whereas t is going to be 16.6 in the case of 60 Hz frequency, and that is going to be 20 milliseconds in the case of 50 Hz frequency. So we'll be able to get the value of average output voltage. And now, if you want to get the ripple in the voltage, then the ripple in the voltage is talking about the minimum value to the maximum value difference. Now you know that the minimum value is at t is equal to T1 and maximum value is exactly same as my source voltage maximum. So now minimum value is nothing but the value of the source voltage. You can see that the minimum value is nothing but, or here the minimum value is nothing but the value of the source voltage at time t equal to T1. The maximum value of the source voltage is nothing but, output voltage is nothing but source voltage max itself. So now if you consider that minimum value of the output voltage is happening at t is equal to T1, and you can calculate as the source voltage itself at t equal to T1, then maximum value of that voltage is happening at t is equal to T by 4, and that is same as the source voltage maximum. Then the difference between this min and max values will give us the ripple in the voltage. So that is delta V is nothing but max minus minimum, which turns out to be 5.8 voltage in this particular case. Let us solve a problem on a half-wave rectifier which is feeding an RL load. In the case of this particular circuit, we have our source voltage having a maximum value of 175 volt, and feeding this half-wave rectifier is feeding a RL load where the value of resistance is 10 ohm and the value of inductance is 40 millihenry. Now in this case, if you want to calculate the time at which the diode stops conducting, also the output average voltage and the output current. In order to get that, we can see that these are the responses for the source voltage, output current, and output voltage and voltage across the resistor and inductor and everything in the case of a half-wave rectifier. Now if you look at that, it is very important for us that if you look at the source voltage and the output voltage, this is what is the output voltage for us. Output voltage doesn't stop exactly at pi, but it is present beyond pi for some more time. This is due to the stored energy in the inductor. Now, if you want to know the average value of that output voltage, it is very important for us to know the time at which the diode stops conducting, because this time is the end time of our average calculations. Now, if you look at the way we derived these expressions, the time at which the diode stops conducting, this is similar to what is the requirement for us to know the time at which the diode starts conducting in case of an RC load. So the time at which the diode stops conducting is solved by this equation. If you are able to solve this equation, which is nonlinear, you will be able to get the time at which the diode stops conducting. Now the clue for solving this particular equation is the diode stops conducting after pi, and it will stop conducting after that. That means if you look at half of your time, so this diode stops conducting from t by 2 to higher values. So now that will be t. So within this range, your diode will be will stop conducting. Now if you substitute that numbers, then whichever the value of t2 that satisfies this equation will be the time solution for us. And in this particular problem, we'll get to know that the time at which diode stops conducting will be 11 milliseconds. So this should range between 8.4 to 16.6 kind of thing. So that is the range in which this particular time exists. Now after getting the value of time, then we can substitute that value of time in this equation. You can see that the average value of the output voltage will be Vmax upon 2 pi 1 minus cos omega t2, because this particular value of pi plus sigma is nothing but pi plus the extra time that the diode is conducting. If you add whole of it, then that is omega t2. We have t2 as 11 millisecond. Omega t2 can be substituted here because omega is 377. Vmax is 175 and pi is a constant for us. If you substitute, then we'll get average value of the output voltage as 42 volts here. And after getting the average value of the output voltage, what we need is the average value of the output current. That we will get simply by dividing the average value of the output voltage with the value of the resistance, because we want average. The inductor is not much affecting the average value of the current there. So 42 by 10 is 4.2 amps is the average value of the output current for us.